Assalamualaikum. Hi, my name is Ani Shakiri Metishaha. My matric number is E24A3283. So today we will gonna do a presentation on geochemical process in soils, rock, and water. We are from Group C. So first of all, geochemical cycle represent the movement or transformation of a particular form of a matter through the living things and non-living things part of an ecosystem. This cycle involves transfer of elements between different reservoirs like atmosphere, hydrosphere, biosphere, and lithosphere. So biosphere encompasses all living organisms and their environment on Earth, forming a complex interconnected web of life. So, example, hydrosphere includes all water on Earth. This includes water from ocean, river, and lakes, water that is underground, or even water in the atmosphere. So next we have geochemical process. Geochemical process have two parts, which is endogenic process and exogenic process. Endogenic process is where process happen internal. It's happen in the subsurface, and whatever below it will come up from volcanic eruption. So first, from endogenic, we have magmatic differentiation, where during cooling of magma, there will be a separation of melt from crystal, and then metamorphism, where chemical will change under pressure and temperature, and then mantle convection and partial melting, where control the movement of magma. Next is exogenic process. It's happen external on the surface. First is weathering, where chemical and physical breakdown of rocks, and chemical weathering, where oxidation, hydrolysis, and carbonation. Physical weathering, mechanical breakdown, freeze thaw, and abrasion. Next, erosion and transport, where there will be a movement of weather materials. Next, sedimentation, chemical element deposited in basins. And lastly, diagenesis, chemical changes in sediment after deposition.
Bismillahirrahmanirrahim. Hi, Assalamualaikum and good morning everyone. I'm so glad for being here. My name is Lili Zakira binti Zarawi and you guys can call me Lili. I'm the number 2 member of this presentation group. So today, I would like to guiding you all through something that we often overlook, which is soil. Now, I'm not just gonna talk about dirt only. I'm gonna talk about soil. Soil is a living and dynamic system. It's breathes, it transforms, and it holds the chemical secret that sustain ecosystem, agriculture, and life itself. So, let's explore more about the field of soil geochemistry. For the first slide, I would like to highlight the title, which is What is soil geochemistry? To begin with, what is exactly soil geochemistry? It's a study of how chemical elements behave and transform within soil system. These elements come from the weathering of rocks, decompositions of organic matters, atmospheric contribution like rain and dust, and of course, the biggest factor is the human activity. At the core of soil geochemistry is chemical weathering, which is the gradual decomposition of rocks and minerals that give rise to and transform soils. For the second slide, we have chemical weathering processes. So let's take a good closer at the main chemical weathering processes. For the first one, we have hydrolysis. This reaction involves water breaking down mineral like feldspar, turning them into a clay, and releasing key nutrients like potassium and calcium. For the second one, we have oxidation. This happens when mineral rich in iron, just like a biotite and pyrites, that react with oxygen and will forming rust color iron oxide. You will often see this in a right tropical soil. So for the last one, which is the third one, we have dissolutions. Here, acidic water dissolve mineral like calcite, releasing calcium and carbonate ion into the soil solution. Each of these reactions change the soil chemical composition and frees up nutrients essential for plant growth. So we move to the third slide, which is about element cycling in soil. After these elements are released, they become part of a nutrient that are crucial for maintaining healthy ecosystem. Nitrogen cycle through processes like nitrification and denitrification, thanks to the microbes and chemistry, so plants can absorb it. We have phosphorus is tightly bound in mineral and become available through weathering. Potassium released from feldspar and mica during hydrolysis is another essential plant nutrient. Some nutrients are taken up by plants, others are washed away by water, and some remain stored in soil particles. This makes soil a dynamic chemical environment. So, we will move to the fourth slide, which is we'll explain about soil profile and horizon. To better understanding this, let's visualize a soil profile, which is a cross section showing layer or horizon. The O horizon is rich in an organic debris. The A horizon combines mineral and nutrients from decomposed matter. And we have the B horizon, which is accumulates things like clay, iron, and carbonate leach from above. The C horizon is weather parent rocks that form the base. Weathering and leaching constantly shift elements between these layers, reshaping soil chemistry over time. Let's jump back after taking a break. So, for the fifth slide, we have role of microorganism. Now, it's all not about rocks and rain. Microorganism also drive soil chemistry. Bacteria will help fix nitrogen from the atmosphere. Fungi can break down mineral particles to access phosphorus. And microbial respiration improves the pH and redox condition, changing how soluble certain elements are. This hidden microbial world is what makes soil so chemically rich and biologically productive. So we move to the sixth slide, which is human impact on soil chemistry. Let's not forget about humans have become a powerful geochemical force. Fertilizer add nutrient, but if used excessively, they lead to pollution and nutrients imbalance. Industry release a heavy metal into the soil like lead and cadmium, which are a very toxic things if it's exposed to the soil. Deforestation and erosion remove protective topsoil and expose a deeper layer, speeding up nutrient loss. So, let's sum up that human activity can improve or degrade soil chemistry that will affect the long lasting for our world. So we have to protect our world, right? So, for the case study, I choose the popular topic, which is acidic soil in agriculture. One clear example is acidic soil in tropical agriculture. In high rain region, leaching strip away base cations like calcium and magnesium, leaving behind acidic ion and aluminum oxide. This acidity can reduce crop yields. To manage this, farmers often apply lime to neutralize the pH and restore fertility. It's a perfect example of how understanding soil geochemistry directly improves the food production. Okay, for the last one. Finally, we come to the end of this topic. To sum up all about soil geochemistry is soil geochemistry is shaped by chemical weatherings, microbials, processes, and human influence. It's control, nutrient cycle, plant health, and even how pollutants behave. And by understanding soil chemistry, we can make a better world and a better decision in agriculture, conservation, and land management. I think that's all from me. As the number 2 member, we will move to the third member to explore how these processes compare with the ones that occurred in rock. Thank you and bye guys!
Hi, my name is Nazwa Mutazima Betty Khairuddin and my metric number is E24A3196. Right now, I'm presenting my part, which is geochemical processes in rocks. Geochemical processes in rocks are a key part of the way things work on our planet. They control the chemical changes that rule the Earth's crust and inner part over timescales of thousands or millions of years. They take place at every stage in the life history of a rock, from the way it forms far beneath the surface, through its changes at the surface, to even when it's weathered, disintegrated, and recycled. Central to geochemistry is the comprehension of how elements move through the different types of rocks like igneous, sedimentary, and metamorphic, and how this movement contribute to the ongoing development of Earth's geological systems. So this slide shows us how rocks are made by breaking them down into smaller parts. Let's start with the smallest unit, which is elements. These are basic substances like silicon and oxygen. When these elements combine, they form a minerals. For example, silicon and oxygen come together to form a mineral called quartz, which is very common in the earth crust. Minerals are solid materials with a specific chemical makeup to form the building block of rocks. In the middle of the slide, you can see three minerals, which is quartz, feldspar, and hornblende. Now, when these minerals mix together, they form rocks. The granite shown on the left is a type of rock made from the three minerals. So, to keep it simple, element makes minerals and minerals make rocks. So, there are three types of rocks, which is igneous, sedimentary, and metamorphic rock. So, for this one, I want to explain about the igneous rock. Igneous rock, which are formed when the molten rock called magma or lava cools and hardens. We can divide igneous rock into two main types based on where they cool. For the first one is intrusive or plutonic rocks. They cool slowly beneath the Earth's surface, forming coarse-grained texture with visible crystal. For example, we can give granite. So the second one is extrusive or volcanic rocks. This one is extrusive or volcanic rocks. They cool rapidly at or near the surface, resulting in fine-grained or glassy texture. So this rapid cooling result in rocks that are fine-grained or even glassy. They will form like a basalt, pumice, or obsidian rocks. So now the other way to classify igneous rock is by how much silica they contain. Silica is a major ingredient in igneous rocks, and the amount of it affects the rock's color, density, and where it forms. So here are the So as you can see, here are the four silica categories. Classic rock have more than 63% of silica. They are usually lighter in color. For example, include granite, intrusive, and rhyolite extrusive. So the second is intermediate rocks have about 52 to 63% of silica. For example, diorite as an intrusive rocks and andesite as extrusive. So the third one is mafic rocks have about 45% to 52% of silica. So these are darker and denser like gabbro and basalt. So the last one is ultramafic rock have less than 45% of silica like dunite. And they are very rich in iron and magnesium. This chart in the middle shows how different rocks match up based on whether they form inside the earth or on the surface, and how much silica they contain. So to summarize, igneous rock form from cold magma or lava, so they are classified by where they cool. And how much silica they contain. So to summarize, igneous rock form from a cool magma or lava. They are classified by where they cool and how much silica they contain. These difference help geologists understand how and where the rocks form. So the second one is sedimentary rock. There are three main types of sedimentary rock, which are formed from particles or materials that settle and get compacted over time. Sedimentary rocks are created when sediments, like pieces of rocks, minerals, or even organic material, get pressed and cemented together over long periods. Three main types of sedimentary rocks. The first one is clastic sedimentary rocks, formed from the compaction of rock fragments, also called clasts. These are pieces of other rocks that have broken off due to weathering and erosion. So the example includes which is sandstone, which came from sand particles, shale made from tiny mud or clay particles. So the next one is chemical sedimentary rocks, from when minerals dissolve in water and then precipitate out, meaning they settle and form solid. This often happens in areas with lot of evaporation. For example, limestone often form from calcium in water. So as gypsum, which can form in salty lakes or sea environments. So the last one is organic sedimentary rocks, come from the remains of living things like plants or marine animals. Over time, these remains pile up and turn into rocks. Two good examples are which two good examples Two good examples for the organic rock, which is coal made from the ancient plant materials and chalk from tiny marine organisms. Move on to the next slide. We talk about metamorphic rock. So metamorphic rock existing occur when existing rocks are changed by heat, pressure, or chemical activity, but without melting. So the rock stays solid, but in minerals and texture change. These changes happen deep underground, usually in areas where tectonic plates collide or near hot magma bodies. So there are two main types of metamorphism. So the first one is regional metamorphism, and the second one is contact metamorphism. The regional metamorphism occurs over large areas, often during mountain building events. In this case, intense pressure and heat cause the rock to recrystallize and form a new structure. For example, shale, a common sedimentary rock, can be transformed into slate and then into a schist and gneiss as the pressure increases. So the second one is contact metamorphism. So it happens when hot magma intrudes into cooler surrounding of rocks. The heat alters the rock's mineral structure, forming a new rocks like marble from limestone and hornfels from shale. So metamorphic rocks often show foliation, which is a layer or banded appearance caused by the reorientation of minerals under pressure. Studying metamorphic rocks help geologists understand the condition deep within the earth and reconstruct past tectonic events. So the crystallization, which is the process that forms igneous rock. This happens when molten rock, called magma when it's underground, and lava when it's on the surface, cools and hardens. So as the molten material cools, atoms begin to arrange themselves into solid mineral crystal. There are two main environments which this can happen, where this can happen. First, if magma cools slowly underground, it allows large crystals to form. So this type of rocks are called intrusive igneous rock. A great example is granite, which you can often see in the countertops or mountain ranges. So the second environment is when lava erupts from a volcano and cools quickly at the Earth's surface. This rapid cooling doesn't give crystal much time to grow, so the rocks end up with a fine grain or even glassy texture. These are called intrusive igneous rock, and basalt is a good example. It makes up much of the ocean floor. So this process is crucial because it is very first step in the rock cycle. Igneous rock form the foundation of the earth crust, and they tell us about the condition deep inside the earth. The type of igneous rock that forms depends on the magma composition and how fast it cools, which geologists can use it to study volcanic activity and plate tectonics. So the next one is chemical weathering. This is a process that happens mostly at or near the Earth's surface. Here, rocks are exposed to the air, water, and natural acids, which react with the minerals inside the rock and change them chemically. So one common example is oxidation, which is similar to how metal rusts. So when iron-rich rocks are exposed to the oxygen, they form reddish or brown iron oxides like hematite. Another example is carbonation. This happens when carbon dioxide in the air dissolves in rainwater, forming a weak acid called carbonic acid. This acid can slowly dissolve rocks like limestone, especially in wet climates, leading to the formation of caves and sinkholes. There are also hydrolysis, where water reacts with minerals like feldspar and turns them into clay. This is especially important in forming soil. So chemical weathering is important because it breaks down solid rock into smaller particles and releases nutrients like calcium, potassium, and iron into the soil and water. These nutrients are essential for plant growth and contribute to the long-term fertility of ecosystem. It's also one of the processes that contribute to the global carbon cycle because it can remove carbon dioxide from the atmosphere over time. So for the last part of my presentation, I'm going to talk about geochemical cycling. This is the continuous movement of chemical elements like carbon, sulfur, iron, and calcium between rocks, water, air, and living organisms. These cycles are essential for keeping the earth in balance. So rock play a big part in storing and releasing these elements. For example, carbon is stored in a limestone and other carbonate rocks. When these rocks are weathered and undergo volcanic activity, so carbon is released back into the atmosphere as carbon dioxide. So this part of the carbon cycle which is regulate Earth's climate over millions of years. Another example is sulfur cycle, where sulfur is released from volcanic gases, incorporated into rocks, and later returned to the atmosphere or ocean through weathering. The subductonic zones also play a key role, where oceanic plates sinks back into the mantle. The sediments and rocks on them carry elements deep into the earth, which are later released again through volcanic eruption. So rocks are constantly being recycled, and with them the elements they contain. So understanding geochemical cycles help us grasp how Earth systems are connected. How a rock forming at the bottom of the ocean today could one day release gases that impact the climate or provide nutrients for the ecosystem.
Assalamualaikum and hi everyone. I am Nur Atira Farihan binti Sudin. Matrix number E24B3382. Now I'll continue by presenting geochemistry in water. So, what does geochemistry in water means? It's the study of how chemical process affect natural water system, including rivers, lakes, groundwater, and even rain. Water is not just H2O. It contains minerals, ions, gases, and even living organisms. Water acts as medium for chemical reaction and carry dissolved ions. Where do these chemicals come from? They come from interaction with rocks, soil, the atmosphere, and also the biological activity. Understanding this interaction helps us explain things like why acid rain damage buildings, or even how pollution spreads through water. Also, what influences water quality in the water body on Earth? how rocks and soil impact chemical weathering. This shows water geochemical is important in understanding pollution, nutrient cycles, and also ecosystem health. For the next slide, hydrological cycle. To understand how water chemical change, we first need to look at the hydrological cycle. Hydrological cycle tells us the movement and the distribution of chemical elements in water across the Earth system. In this case, elements will undergo separation and then recombination in different reservoirs. This diagram attached here shows the full hydrological cycle, which is the continuous movement of water. In this case, elements will undergo separation and recombination in different reservoirs. This diagram attached here shows the full hydrological cycle, which is the continuous movement of water through different parts of the Earth system. First, we have evaporation and transpiration. The water from the oceans, rivers, and lakes will evaporate due to heat from the sun. Plants also release water vapor through transpiration, which together we call evapotranspiration. This water vapor rises into the atmosphere and eventually condenses to form clouds. Then comes precipitation. When the atmosphere can't hold any more moisture, water falls back to the Earth's surface as rain or snow. But precipitation doesn't just land in rivers, it can also fall on soil, rocks, and forests. And from there, several things happen. Next is infiltration and runoff. Some of the water infiltrates the soil, moving downward until the groundwater. Other water flows over the surface as runoff, go into the streams and rivers. This surface runoff can erode rocks and pick up sediment and minerals along the way. Under the ground, water slowly moves through cracks in the rocks and also soil, a process called groundwater flow. During this time, water can spend decades to thousands of years underground, react with rock minerals, and also will pick up ions like calcium, magnesium, sodium, and more. And then for snowmelt and volcanic, happens in cold region. Snow will melt to the streams and river. Meanwhile, volcanic stream contributes water vapor or gases into the system. So what does this have to do with geochemistry? As water moves through the entire cycle in the atmosphere, on the land, and below ground, it doesn't stay pure or original. It will interact with soil, rock, gases, and the biological material. This interaction changes its chemical composition, which is what we study in geochemistry. So in this cycle, water is not just moving, it's reacting, dissolving, transporting, and shaping the earth. Now I'll go deeper into the actual process that changed the chemical in water. Geochemical process in water. First is dissolution. Dissolution happens when minerals dissolve into the water. In this process, ions will release. Halide, for example, dissolve and release sodium and chloride ions. That is basically natural salt entering water. Another example is gypsum, dissolve and release calcium and sulfate ions. The next one is hydrolysis. Hydrolysis is when there is reaction of minerals with water and carbonic acid that forms clay minerals and also dissolve ions, like in attached chemical equation. As an example, water reacts with minerals like feldspar and turn them into clay soil. Lastly, oxidation. Oxidation happens when minerals that contain iron react with oxygen in the water. It is a chemical reaction where ferrous ion oxidizes to form ferriion. This reaction makes it possible to see red or orange color stains on rocks or soil. That is oxidized iron, or we call rust. It changes not just the rock's appearance but also affects the pH and metal content on the surrounding water. Next, chemical weathering into water. Chemical weathering is a major contributor to water chemistry. It is when any minerals go through chemical reaction with water and gases. In weathering, ion will release into waters. These ions not only affect water quality but also decides that water is suitable or not for like agriculture, fish habitats, or even for household. So whether we see it or not, chemical weathering plays a huge role in shaping the water we use and the land we live on. Now let's read through 3 sources of weathering. First, from mineral. Weathering will release ions from minerals in rocks into water. Silicate rocks like granite breaks down slowly, while carbonate rocks like limestone dissolve faster. Next, for carbon. Carbon dioxide from the atmosphere dissolves in water, forming carbonic acid, which is a weak acid. This acid is enough to dissolve limestone or feldspar over times. In natural carbon cycle, it helps to remove carbon dioxide from the atmosphere and store it in the ocean. Lastly, from soil environment. Soil is actually an active chemical zone. Organic acids from roots can increase the acidity of water, make the weathering process faster. As water passes through soil, soil will absorb nutrients from ions in water, which they are important in agriculture. This will affect pH, water retention, and chemical composition of runoff and groundwater. Next slide, factors affecting chemical change in water. Several things controls how quickly water chemistry change due to weathering. First factors is parent rock types. Some minerals dissolve quickly in water, for example, limestone, while others are more resistant, like quartz. The second factor is climate. Warm and wet climates may speed up chemical reactions. In contrast, cold and dry weather slow the process down. Next one is pH and temperature. Lower pH means more acidic, and higher temperature can increase reaction speed. While higher pH, which is alkali, will lower reaction speed. Lastly, biological activity. Microorganisms and plant roots produce acids that help break down minerals faster. As an example, tropical rainforests have fast weathering due to heat, moisture, and plant activity, while deserts have slow weathering. Understanding these factors help geologists predict water quality and mineral availability in different regions. To conclude, geochemistry in water always happening, breaking down rocks, moving the ions, supporting the ecosystem, and even shaping the climate. That's our geochemical process in water. Thank you.
So to conclude, from what we learned, we know that geochemical process play a vital role in shaping the earth structure, composition, and environmental system. This natural process, such as weathering erosion, mineral formation govern transformation of chemical element in the earth crust, ocean, and atmosphere. And we know that understanding geochemical is essential for predicting natural hazard, managing natural resources, and addressing environmental challenges such as pollution and climate change. This is our reference. That's all from us, Group C. Thank you.